Good morning, Mananal. I'm Fathima Fasna, a full-time research scholar in the PG and Research Department of Chemistry, Maharaja College, Ernakulam, under the guidance of Dr. Srisha Shashi, Associate Professor, PG and Research Department of Chemistry, Maharaja's College, Ernakulam. So, this session is a part of Research Scholar Webinar Series 2021 that is conducted by Research Committee and IQAC, Maharaja's College, Ernakulam. And today's session is about metal organic framework, a versatile class of advanced material. So let us start our session. So the topic is metal organic framework, versatile class of advanced material. So before digging into the subject, that is MYF, let us discuss what are called nanoporous material. So, a nanoporous material consists of a regular organic or inorganic framework supporting a regular porous structure. And these structures with uniform pore distribution offer new properties such as adsorption, absorption, exchange separation, etc. And depending upon the pore size, these nanoporous materials are divided into three classes. As we can see, there are microporous substances in which the pore diameter is less than 2 nanometer, and we have mesoporous substances in which the pore diameter is in between 2 to 50 nanometer, and we have macroporous substances that are having a pore diameter greater than 50 nanometer. And now, these are the examples for nanoporous materials. What are they? Zeolites. These zeolites are the most common one, right? Then we have MOF. MOF is the metal organic framework. And we have POF. POF is a porous organic framework. And now, zeolite. Among all those three examples, zeolite might be the most familiar one, right? So, zeolite is the most common example for a nanoporous material. And zeolites are actually aluminosilicates having a porous structure and large surface area. And they have highly ordered discrete pores or cavities with molecular dimensions in which small molecules, small substances like gas molecules can pass through while blocking the large one. Therefore, they are termed as molecular seals because they can block small molecules that have their dimension, the pore dimension, and leaving behind the larger ones. So, they are also termed as molecular seals. And these pores can also absorb or desorb water molecules or gas molecules without destroying the overall structural framework of the substance. And next comes the POFs. POFs are the porous organic frameworks. And actually, this POF is a general term for different covalent organic frameworks like covalent framework, porous or aromatic frameworks, etc. And actually, this POF comes from organic molecules with strong covalent. And it has remarkable features like large permanent porosity, high thermal stability, and also these properties like high thermal chemical stability, porosity, and they can be employed in gas storage, gas separation, catalysis, etc. And now comes metal organic frameworks or MOFs. So this metal organic framework, and it is usually abbreviated as MOF, and it's coordination polymer or a coordination network with an containing large or voids. That is large channels or vacant spaces are not. And these substances that contain inorganic metal ions or clusters of metal ions that are coordinated to organic ligands to form one dimension or two dimension or three dimensional structures. And also they have a very unique properties like low surface area, external porosity, chemical tailorability, and luminescence. And this is basic structure of an MOF. So, a basic structure of an MOF is composed of two major components. A metal ion, the first component, or metal cluster, that like a base cluster. So, it is a major component, one of the major components And the second component is an organic ligand. So the organic try or tetravalent ligand. So this is the basic structure of a metal organic framework, which contains only two parts, only two components: a metal ion or the metal cluster and an organic. Next is the structural features of an MOF. First one is they have very low density. Why? Because they have highly porous structure, right? They contains high pores, I mean large number of pores or voids within them. So they have very low density, and they have very structure because of the strong interaction between the cell and the ligand. They have structure, and so as we already discussed, they possess large and have wonderful interaction between the constituents. What are the constituents? The metal ion and the ligand. So they have significant wonderful interaction between the constituent within the framework. And also, finally, they have very complex unit cell. It contains a very complex unit cell. Now, we are already discussed that these MOFs have got highly porous structure. Now, what will be the importance of this pores or the size or dimension of this pores? This is what we're gonna discuss now. Now, many potential applications of an MOF like gas capture or gas storage or catalysis, etc., will depends upon the size and nature of this available free space. These available free space known as pores or voids. So, these applications, more the number of pores or the more the size of the pore, more will be the potential application of this MOF. And now the pores can actually, we can tune these pores or we can customize these pores. And this tuning of this pores is typically achieved by varying the metal ion, that means by changing the metal ion or by changing the ligand, and also by lengthening the organic chain or by lengthening the chain length of the ligand, we can also increase the pore size. But there's a limitation in that, because by lengthening the chain, by lengthening the organic ligand, the overall framework stability will be get decreased. So there is a limitation in that. And also in 2017, Babali et al. He is a chemist, and he and his group, Babali et al. Investigated the effective pore size and shape on thermal conductivity of a series of idealized MOFs containing adsorbed gas using molecular simulations. So they used molecular simulations to determine the effect of pore size on the thermal conductivity. And for that, with no gas present, the thermal conductivity decreases with increasing pore size. And in the presence of adsorbed gas, the MOFs with smaller pore size experienced reduced thermal conductivity because of the photon scattering induced by the gas crystal interaction. But in contrast, for MOFs having larger pores, the adsorbed gas doesn't significantly affect the thermal conductivity. So this might be due to the decreased probability of gas crystal collision in the larger pore, because there is enough room for all the gas particles to get inside. That will be the reason why the pore size doesn't affect the thermal conductivity. And let's move on to the properties of MOFs. What are the properties of MOFs? First of all, the framework of MOF consists of metal ion that act as connectors and organic ligand as a linkers. So the metal ion or the cluster of metal ion is a connector and organic ligand is a linker, which is connected to the connector. And these MOFs have a regular array of pores which are readily accessible, which we have already discussed. And also they have a hydrophilic metal center. These MOFs have hydrophilic metal center and hydrophobic linker moiety that will influence their adsorption properties. So both the hydrophilic part and hydrophobic part are present in this MOF. So this will surely influence the adsorption properties of these MOFs. And the next point is that most of the MOFs have very low electrical conductivity. because due to their weight structure and all. And this limit their utility in the technologies like a fuel cell, supercapacitors, thermoelectronics, etc. But in past several years, several works have been done by several chemists to develop electrically conducting MOFs. For example, in 2009, Takashi reported the first electrically conducting copper MOF, which is electrically conducting. And we're talking about the thermal stability of an MOF, and this thermal stability of an MOF will depend more upon the coordination number and the coordination environment rather than the framework topology. And as we already discussed, there are poor thermal conductors with thermal conductivity, which is similar to concrete. Concrete that we also, as we all know, is a thermally insulator one. So they have very low thermal conductivity, just like concrete. Now, the synthesis part. We are moving on to the synthesis part of the MOF, which is very important in the research work. So, synthesis, there are 5 major synthesis methodologies for this metal organic framework. First one is a solvothermal method. So, in solvothermal method, it is most recurrently used method for the preparation of an MOF. And in this method, the solution of metal salt and the organic ligand in a suitable solvent will be heated, usually in an autoclave. So we'll get a product. So this is the solvothermal method, just the heating of metal salt and the organic ligand in a suitable solvent in an autoclave. Next method is a microwave assisted synthesis. Microwave assisted synthesis. It is a swift method for the synthesis of MOF. And nano-sized crystals will be produced by the irradiation of reaction mixture with a microwave. And the advantage of this method will include high efficiency, less reaction time, particle size reduction, etc. And the next method, the third method is ultrasonic irradiation, or simply we can say sonochemical synthesis, by irradiating the reaction mixture with ultrasonic radiations. So this ultrasonic radiation can actually create very high temperature and pressure in a reaction medium. And also this reaction will be rapid, economical, eco-friendly and reproducible. And the next method is electrochemical synthesis. And in electrochemical synthesis method, the metal ions are provided through anodic dissolution into reaction mixture that containing the organic liquor. And major advantages of this method is that the anion which is associated with the metal ion salt can be avoided because the cation is provided through the anode dissolution. So anion is avoided completely, and hence the material synthesized, the product will be in high purity. We'll get a highly pure product because the anion is omitted from the reaction mixture. Right. And the last method is mechanochemical method. Mechanochemical means it's just the method in which the chemical reaction is done with the help of the mechanical force. We are using a mechanical force for the completion of the reaction. And major advantage of this mechanical method is the reaction will take place without any toxic organic solvent. We doesn't need any solvent for the reaction to conduct. That's all about the synthesis method. 5 major synthesis method for the preparation of MOF. Now, what is the chemistry behind this MOF? What is the chemistry of this metal organic frameworks? First of all, organic ligands are ditopic. Ditopic means they can coordinate to the metal cluster or the metal ion in 2 different sites. Therefore, these organic ligands are, we can say, ditopic. Or we can use multi-topic linkers also. Multi-topic means they can connect the metal center or the metal cluster to multi-topic linker. And the third point is that the bond between the metal ion and the liquor is quite strong. That's why we said that they have a highly crystalline structure, or the van der Waals interaction is strong. We have already discussed that, right? So the bond between the metal ion and the liquor is quite strong, and hence the overall framework will be very robust. That means very tough, very crystalline. And the next point is that secondary building unit. Secondary building unit or SBU is a very important term in metal organic framework. And actually, this SBU is just a cluster or is just a complex that is formed by the metal ion and the donor atom of the linker, and it is just that complex, and it is very important in metal organic frameworks because this SPO is something that determines the topology, final topology of this MOF. Okay, so the SPO is one important word in metal organic framework. And talking about the active site is actually the active site in an MOF is exists at metal node of the framework. Metal node, the active site is exists at the metal node of the framework. And during the course of the reaction, the framework will protect the active site, which is at the metal site, and thus it will increase the efficiency of the reaction. And the next point is that we can use different metal ions, and usually we use transition metals as the inorganic center. And when we use different metal ions, it will yield different metal organic frameworks with different coordination number and different geometries like tetrahedral, T shape, Y shape, octahedral, pentagonal. Any shape will get different geometries of MOFs while using different metals or metal clusters. And also on choosing the organic ligand, when we come back, coming to the organic part, when we choose the organic ligand, the one with a rigid backbone will be get chosen. Why? Because the rigidity of this organic linker will help in the prediction of the network geometry. And also, this will help to retain the open pore structure of this metal organic framework upon the post-synthetic solvent removal. So when we remove the solvent from this voids of this metal organic framework after the synthetic processes, this rigidity of this organic linker will help to maintain the pore dimension, the structure of the overall structure of the metal organic framework. And talking about the application of MOF, we have handful of applications for this MOF like gas separation, gas absorption, ion exchange, gas purification, catalysis, hydrogen storage, biomedical applications, sensing. Many number of n number of applications are available for MOF, metal organic framework. Now we are going to talk about the literature survey. Okay, the literature works that have been done on MOF till this point. This is the first ever discovered MOF5 or MOF5. So it was reported by Omariaki and his team in 1999. And they used zinc oxide as the inorganic part and benzene dichromic acid, benzene BDC, benzene dicarboxylic acid as a diatopic ligand. And this picture, what you can see on the screen, this is a rigid structure of the MOF5. And these yellow balls, these are actually the voids or the vacant spaces in between this the framework structure of this MOF5. And these vacant spaces can be accommodated by small molecules or gas molecules and all. And the surface area of this MOF5 was found to be about 2,900, that is 2,900 meters square per gram, which was the highest among all porous material that was found up to that point. And when we talk about the surface area, 2,900 meters square per gram, it just means when I take a gram of this substance and I spread it on a flat surface, actually it would cover the whole football ground. There was that much of porous structure. Like when I take 1 gram and I just spread it on a football ground, it will fill the whole football ground. And this is just the nitrogen sorption isotherm for the MOF5 network. Now, The second work the second example is this is the latest work that has been done on metal organic framework and how et al. This is a work of how et al. How and his co-workers in 2021, which is very recently in 2021. They have synthesized a nickel MOF by solvothermal method and they performed a mixed gas separation using this particular MOF, and the MOF displayed excellent separation performance among ethylene methane mixture, ethylene ethane mixture, ethane methane mixture, carbon dioxide methane mixture, etc. And the figure shows the three-dimensional cross section of this particular nickel MIF, and the yellow and the blue balls, of course, it gives the voids or the free channels among the metal organic frameworks or within the metal organic framework, and it's these are the breakthrough plots, just the breakthrough plots of and these several metal organic frameworks upon the separation of ethylene and carbon dioxide. So the plot A, it gives a breakthrough plot for the separation of ethylene and carbon dioxide mixture, which is equimolar, equal amount of ethylene and carbon dioxide are taken, and they employed different metal organic frameworks for the separation, and this was the result that they have obtained. And it is very clear that so this red one is the result of the and the blue one is actually is a result of MIL 101 CR. It is a reported metal organic framework, and the green one is that of some copper MOF, and the blue one is that of the HCUST one, which is a reported metal organic framework. So from the breakthrough plot, it is very clear that the separation ability of this particular nickel MOF is greater than that of HCUST1 and copper MOF, right? And moving on to the second breakthrough plot. When we talk about the second breakthrough plot, it just gives a separation ability of this particular nickel MOF upon different concentration or different ratios of ethylene and carbon dioxide. So as we can see, it shows very good results for the separation. That means it can separate different concentrations or different ratios of ethylene and carbon dioxide mixture. And the third example is that this was work done by Yang et al. In 2016, and they actually prepared a cobalt MOF nanosheet for the first time. A nanosheet is made from cobalt MOF for the first time, and actually this material was used as an electrode for supercapacitor. A supercapacitor electrode which showed very high specific capacitance. And the good electrochemical properties might be due to the intrinsic characteristics of cobalt MOF, such as layered structure or the conductive network framework or the nanosheet structures, etc. And the figure shows the SEM and TEM image of this surface of this particular cobalt MOF. And this is a cyclic voltammetry curve of this cobalt MOF at various scan rates. So that's all about the literature surveys or the literature review upon the metal organic framework. Now, talking about the scope of future work, we have actually a notion of opportunities for the research in metal organic framework, because there are lot number of applications that are waiting for us, like supercapacitor, like hydrogen storage, catalytic activity, electrochemical energy storage and conversion, pollution control. A lot number of applications are possible in the case of MOF. So we have ocean of opportunities for the application of MOF. So that's all about the session, and hope you all understood, or hope you all like what I have conveyed to you. And I extend my sincere gratitude to Dr. Srisha Shashi for her immense support and guidance. And I also thank Jomol Pijon, Dinsi, and Naufia and Preeta. We are all research students of chemistry department, Maharaja's College, and I thank all of their support. And I hope everybody understood or everybody have got advantage of my session. So thank you all. Thank you.